Hello everybody, welcome back to another video, and in this video we'll be looking at the natural logs of complex numbers. So for instance, let's look at something a bit simpler, and that is the natural log of -1. So we know that natural log in the real world is defined for only positive integers or positive numbers. However, when we take the natural log of -1, what are we supposed to do? Because by definition, we're saying that e to some x is equal to -1. And of course, we know that that is not possible because if we see the graph for e to the x, for instance, we'll see that the y values always stay above 0 because when you have some real number to any real power, you cannot end up with a negative number. And now, how are we supposed to do this? And this brings us to complex polar coordinates. So let's go to the complex plane now. And what we see is in the complex plane, we have the y-axis represented as the imaginary axis. So it would look something like this, where we have the imaginary axis here and the real axis here. And when we have some complex number, which is written as z is equal to a plus bi, which is the standard form of a complex number, let's say that's some point here. To convert this into complex polar coordinates, we need to first establish how to convert with normal polar coordinates. So we know that we can represent some a being equal to r cosine theta and b equal to r sine theta. And of course, you can derive this from the unit circle by seeing in a unit circle of radius 1, you'll see that this length right here is going to be r sine theta, or it's just going to be sine theta, and then this length right here is going to be cosine theta. And then when you have a circle of radius r, the lengths are going to be r sine theta and r cosine theta. So now what we see here is that we can substitute our values for a and b into the standard form of a complex number to see what we get there. So we see that z now is equal to, substituting a, we get r cosine theta plus bi, and b we can see is r sine theta, and then we have an I, so let's put ri sine theta. Now what we can see here is that we have an r in each term, so we can factor out the r. We see that we have z is equal to r, and then we have cosine theta plus, and then we still have an I left over, sine theta. And does this look familiar? Well, it should, because this is Euler's formula, which we all know as e to the I theta is equal to cosine theta plus I sine theta. So what we can see here is that we can very nicely just replace this entire expression with e to the I theta. So we can see that z here is r multiplied by e to the I theta. And of course, how do you compute the values for r and theta? Well, let's say you have this point here. The value r can be computed by the distance of that point from the origin. So we know that by Pythagoras, if we draw a triangle here, it's just going to be, let's say this is b, this is a, it's just going to be the square root of a squared plus b squared. So we can write that down here. We can say that r is going to be equal to the square root of a squared plus b squared, and our theta is the angle from the positive x-axis, so that would be this angle. And to calculate that, we see that we have two side lengths, the opposite and the adjacent, so therefore we need to use the tangent, and to get the angle theta, we need the inverse tangent, and tangent opposite over adjacent, so we have b over a. So these are all the values that we have. And this will be useful for the upcoming problems that we look at in today's video, and will not help so much with this first problem as it's slightly easier. So let's go back to the natural log of -1. We know that -1 will be right here on the complex plane. So let's say this is -1, let's say. Then what do we know, as this is directly intersecting the real axis, the distance from the origin is just going to be the absolute value of whatever that number is, which is 1. So we know that r is 1 here. We don't need to calculate anything there. And to get theta, well, we know theta is the angle from the positive x-axis, so it would be this. And we see that, of course, this is the angle formed with a straight line, which we know is 180 degrees, or you can write this as pi radian. So theta is pi. So now what we can do, we can use our now new form of writing a complex number. And we can say that here, -1 is equal to r e to the I theta. So r is 1 multiplied by e to the I theta is pi. And what we see here is that -1 can be written as e to the I pi. And this is, of course, where you can see Euler's great Euler's great formula or Euler's great identity, where we see e to the I pi plus 1 is 0. Of course, that comes from here. Adding 1 on both sides, you get e to the I plus 1 is 0. So that is pretty cool, but now how do we get the natural log of negative 1? So what we can see is that the natural log of negative 1 is nothing but just taking the natural log of e to the I pi, like so. And we know that by definition, the natural log is the log base e, so we have the natural log of e to some x, that those will cancel out, and you're just left with that x. So you're just left with I pi. So therefore, the natural log of negative 1 is I pi. But actually, that is not the entire story, and there's actually more to this, because if we go back to the complex plane, we see that this angle here, which we know as pi, what happens if we add 2 pi to that? So that means doing a full 360-degree rotation. Well, we just end up at the same point. And what happens if we go back twice 360 degrees, or minus 4 pi? Well, you would just end up at the same point again. So what we can see is that we can keep on adding some multiple of 2 pi, or subtracting some multiple of 2 pi. So what we see here is that when we're dealing with the complex numbers, an angle can always be described as that angle plus 2 pi n. So 2 pi n, where n is an integer, because we can keep on adding or subtracting multiples of 2 pi to reach the same angle, to reach the same point on the plane. So what we see here is that in reality, negative 1 is actually just I. It can also be written as I and then pi plus 2 pi n. And then therefore we can see that negative 1 is I pi plus 2 pi n, like so. And therefore we need to actually change some things with the natural log, although not much needs to be changed. So when we take the natural log of negative 1, we're now taking the natural log of e to the I pi plus 2 pi n. And here, the natural log and the e still cancel out, and we're just now left with I pi plus 2 pi n. And this is the final answer that we see for the natural log of negative 1. And the final concept to introduce here is the idea of branches. And to understand branches, first of all, let's establish some just one piece of terminology. This angle here, theta, that corresponds to the angle here, is called the argument. And to understand what branches are, well, the idea is that a branch is a continuous function that selects only one value from the results of the multivalued function. So for instance, this is a multivalued function right here, because the natural log of a negative number results in an infinite number of solutions. So to take a more simple example, if you look at the square root function, if you look at 2 squared is always going to be 4. However, if you look at the square root of 2, and you're, for instance, saying that x squared is 4, and then you're taking the square root on both sides, you will have positive or minus 2. And a branch of the square root function would be a continuous function that selects one of these values for each input. So, for instance, one branch of the square root function might always select the positive root, while another might select the negative root. And in our case, when we're dealing with complex logarithms like so, as this is, of course, multivalued, and it, in fact, has an infinite number of solutions, because you can differ by multiples of 2 pi and 2 pi I, then there are different branches which you can take that are all like continuous functions that select a specific value of the logarithm. So there's also now the idea of a principal branch, and the principal branch is what holds the principal value, which is bounded by negative pi to pi. And this means that it includes pi but does not include negative pi. And this means that the principal value will be held, the argument will be held between or in this interval. So, and this helps us make the function as similar as possible to the corresponding real function. So what we see here is that in our case, to get the principal value of this result of the logarithm, we need to set n to be 0, because if we set n to be 1, we'll get 3 pi, which is not in this interval, and if we set n to be negative 1, we'll get negative pi, and this does not include negative pi, so our n must be equal to 0. So this I'll make a note of is the this is the principal branch. And what we see here is if we take the principal value, we let n equal to 0, and we see that the natural log of -1 is equal to simply just I pi. And here, just something else that may be useful, we can also factor out the pi here. I just noticed, so we can write this as I pi, and then factor out here, we still have a 1 plus 2n, where, and then n is an integer. We have to make a note of that, so we can also box this if we want. And the final idea to introduce here is when you have different bases, when you're taking the natural logs of negative numbers. So let's look at a quick example. So let's say we had now the natural log of let's say we had the log base, of -4, and our value is -64. So how do we figure this out? And on first glance, this looks pretty weird because we have negative number in the base and the value. However, when you look at what the definition of the logarithm really is saying, we're saying that -4 all to the power of some x that we're trying to find out yields -64. Now the first thing we notice is that 4 to the power of 3 is 64 indeed. And if we have some -1 to the power of an odd power, which is 3 is an odd number, that will always yield -1 because you have -1 to the 2n times -1 to the first power. This will be 1, and then 1 times -1 is always -1. So then here we know that this will always be a negative when we raise this to an odd power, and -4 to the power of 3 will be -64, which is exactly what we have here. So a valid solution to this logarithm is x is equal to 3, because -4 to the power of 3 is indeed 64. However, there is more to this that I will elaborate on later. So now let's look at another example where we have the log base +4 of -64. Now, how much worse can this be? And indeed, this is actually much more difficult because we are saying that 4 to the power of some x is equal to -64. And we know that this is not possible because when we have some a to the x where a is greater than 0 and x is within the real numbers, then we know that this expression must be always greater than 0 as well. So therefore, this is not possible with real solutions. So that's why we need to go to the complex world. And guess what the base is in the complex world? Well, we always use a base e. So then what we will want to do is ideally have a natural log. And how do we have that? With a change of base. And we know the change of base formula when we have some log base k of some a. We can use the change of base formula to see that that's log base c of a over log base c of k, where c is the base you desire. And in our case, it's base e because that is the natural logarithm. So we can see that this is equal to the natural log now, assuming that we've done our change of base and show the working. This is equal to the natural log of -64 over the natural log of 4. Now, what we also know is that this is the same thing as -1 times 64. And we know that a product of two things in a logarithm can be broken into the sum of each thing, sum of the logarithm of each thing. So this can be broken down into the natural log of -1 plus the natural log of 64. And that's all divided by the natural log of 4. And we see that this is indeed true because when we have a summation of two logarithms, multiply them, this indeed does simplify to the natural log of -64. Now, we've already calculated the natural log of -1, and that happens to be, of course, I pi as the principal value, but in this case, we'll put down the general form. So what we see here is that this is equal to, now we have I pi plus 2 pi n to be the answer to that, and then plus the natural log of 64, and then that's all over the natural log of 4. Now, what I also noticed, so I guess we can do that. And then what can we do to simplify here? Well, we know that this is the same thing as 4 cubed. So this part right here, if we zoom in, this is the natural log of 4 cubed. And we know that if we have the natural log to some x to the r, we know that's the same thing as r times the natural log of x. And that is a property for all logarithms. This is equal to 3 times the natural log of 4. So what we have now is, let's just write this as 3 natural log of 4 plus I, and then pi plus 2 pi n. And let's just make a note here that n is an integer. We have integer multiples, and then that's all over the natural log of 4. And what we can finally do is we can split the fraction and see that here this and this will cancel, and then we'll just be left with this over this. So what we have here is 3, and then this over this is 1, so that's fine, plus, and then we have I, and then pi plus 2 pi n all over the natural log of 4. And that is our answer. Now let's go back to our example using the same idea where we have the natural log base, or where we have, the log base -4 of -64. Now to really understand this better and understand how these branches work, let's try using that same method of changing the base. So this is now equal to, we know, the natural log of -64 over the natural log of -4. Now guess what? Let's do the exact same thing to the numerator and the denominator. That means applying the same idea of breaking down the logarithm into the summation of each of the logarithms, given that this is -1 times whatever that number is. So this is now the natural log of 64 plus the natural log of -1 over the natural log of 4 plus the natural log of -1, of course. Now computing each of these, we know that natural log of -1 will be the same. However, what we have to consider is that the multiples that the argument differs by can be different for each of these natural logs of -1. So we'll have to use different variables to represent them. So we have the natural log of 64, then we have I pi plus 2 pi n. So let's just keep it as that. I pi plus 2 pi n. And that's over now the natural log of 4 plus, and then we have to say now I pi plus 2 pi m, for instance, or any other letter, because n is being used here, and if we use an n here, we're saying that the integer multiples are the same, which they don't have to be, and in our case, to reach our desired answer, they will be different. So where do we simplify from here? Well, of course, we use the same idea of just breaking this natural log of 64 down into the natural log of 4 cubed, which is the same thing as 3 times the natural log of 4 once again. So what we have now is 3 times the natural log of 4 plus I pi plus 2 pi n, and let's just make a note here where n is an integer and m is also an integer, but they are not the same, but they can be the same, and that's all divided by the natural log of 4 plus I pi plus 2 pi m. This is a long expression. Now, the final thing we can do, so we can essentially box this now. We can split the fractions or whatever you want to do, but this is a good enough answer for now for a general form. However, to get our desired answer of 3, which is what we computed earlier over I guess here, we got 3 as our answer, and we saw that that is correct. So how do we get 3? So what we do here is we let n equal to 0, because what we want to have is some case where we have the natural log of 4 and the natural log of 4 cancel out, and we have some simplifications here cancel out, and you're just left with 3, because we already see that we have a 3 here, so we're onto something. And if we let n equal to 0, then what we end, or let's say, okay, wait, that won't work. Let's set m to be 0. And if we see that when we set m to be 0, we will just have I pi. And if we set n to be 1, we will have pi plus 2 pi, which is 3 pi. Now what we see there is that we have a 3 and a 3. So let's just write this down. So we have 3 natural log of 4 plus, and now we have I times pi plus 2 pi, and that's over now the natural log of 4 plus I pi plus 2 pi times 0. We know that this will cancel out and this will group to be a 3 pi. So this is equal to 3 times the natural log of 4 plus 3I pi, I guess you could write it as, and here you have the natural log of 4 plus just I pi. Now, what we can do that is pretty cool is we can just factor out the 3, and we see that here we have 3, we have the natural log of 4 plus I pi over the natural log of 4 plus I pi. Wait a second, hold on, these are the exact same, and we can indeed safely cancel them out. The coolest moment of this video, cancel and cancel, and what we're left with is just a 3. So that is pretty cool. That shows that how we take, if we take the different branches of each of these distinct multivalued functions, then we can actually reach answers that indeed have real, are of real value, and also what we computed earlier. So just a quick recap of everything we've done today. We saw the natural log of -1 by introducing the complex polar form of a complex number, or the polar form of a complex number, and that of course comes from using the standard form of a complex number and Euler's formula. Then what we introduced is the idea of adding 2 pi ni, or adding multiples of 2 pi to the argument to produce the same point. So we could have theoretically also gone from here and reached the same point. Of course, then that would be negative pi, and of course that is pi minus 2 pi, of course. So then what we saw is that the natural log of -1 is nothing but the natural log of the complex polar form of -1, which happens to be of base e to some exponent, and we know the natural log of e to something will just return that thing. So here we created a general form, and we made a note, of course, that the multiples will of course be always multiples of 2 pi, therefore meaning that n has to be an integer. Now we also introduced the idea of branches, which are different, which hold different values of a multivalued function. Of course, the principal branch now is bounded by -pi to pi, and taking the principal value is when the argument is in that interval. And we saw that with the case of natural log of -1, that would be I pi. And then finally, we looked at these two examples of taking the logarithms with different bases, and what we saw is that the change of base formula helps us a lot, and we can actually, when dealing with natural log of larger negative values, we can split it up into -1 times that positive value. So if we have the natural log of some -5 or -a, just to generalize it, that's the same thing as the natural log of -1 plus the natural log of, and then a, of course, which is just I pi plus 2 pi n plus the natural log of a. And of course, a here has to be greater than 0 for this formula to work, of course, because we're taking -a, so it has to be like 5, for instance. And then we saw that when taking different branches of these multivalued functions, we can actually reach a desired real output. So anyways, that was it for today's video, and thank you for watching.